Hello everyone. Today we discuss contest 17. Pretty hard contest actually. Especially the last problem. Again, I picked some random problems without much looking about what the problem is about. So sometimes difficulty shown by code forces uh, do not correspond. Okay, it corresponds, but not that accurate, I would say. So maybe gap between these two problems is too high. But some okay, uh, Alex managed to solve the last problem, but not the problem G. But I think problem G is actually much easier than problem H. But it needs some math in problem G maybe, but not in problem H. Hmm. So for some people maybe problem H is easier than problem G because problem H is just data structures. In G you need some mathematics. Maybe, but overall contest it's very difficult, I would say. So a lot of people solving many problems is a very good result. Like before, I recorded myself solving all the problems, so we'll just watch the recording. First problem is pretty straightforward. You have some results of the game and you need to find who is the winner. So you have basically two teams and you need to find which one appears more frequently in the given input. So just read the input, count how many times both strings appears, and find the maximum. Again, many ways to do it. I would do it like this. I'll just make map from string to int, or this map of counters basically. Yeah, and so I will count how many times I see each string, and then here just brute force to find the maximum like I usually do. So you have this result. If you have the string which is appears, this is the frequency. So if it appears more frequently than my string, I will just replace the result. That's how we usually find maximum in array. Yes, so that's it. So I try to do it as easy as possible. Here I check why I have warnings, because sometimes CLion give me some good advice about the code. Here's actually no. So say const auto. Okay, I can do it like this. It doesn't matter for it. You just have two variables. So that's it. That's problem A. Pretty straightforward. Just implementation. Again, it's not the easiest implementation. So if you're not good with data structures, not good with your language, you may have some problems operating with strings, and you need counters. So you need some kind of, you can use map, or you can use just basically two variables. Since you have only two possible strings, you can just find two different strings and count how many times you see each one of them. Also possible. So many ways to implement it. Just I would say it's like exercise of your programming language. So if you're good enough in your programming language, should have no problems with problems like this. Let's go to problem B. Problem B is basically also just implementation, but it's more complicated one. So you need to read problem statement, understand what's going on, and then just basically do what need to be done. So you have a string of zeros and ones, and every segment of ones, continuous sequence of ones represent one integer. You need to find these continuous segments and replace them with this corresponding length. Yeah. Show me. So here's my program. So what I'm doing, how I'm doing it. So I go from left to right, and basically this C variable maintain the length of my current sequence. So I go from left to right. If I see 0, I stop my current sequence and output its length to the output here. And when I see 1, I just increase the length of the sequence. Also, I do it like this. So since the last sequence of ones is not finished with 0, I just add this 0 in the beginning. See here. So I don't have this special case. So now my input like this. I have sequence of ones, then 0, sequence of ones, then 0. And you basically just replace each sequence with the length of the sequence. That's pretty much it. So that's nothing to think about this problem. So again, problems like this, the idea of giving problems like this is to give you a chance to find the easiest implementation. Yeah. So you need to spend as little time as possible solving this problem. So if you're good with your language, if you're good in programming, you just do these problems really quickly and then go to hard problems. If you're not as good as in programming yet, yeah, So you just spend more time, but you learn something. Yes, you learn how to write these programs and stuff. So it's okay if you spend some time solving these problems. So you shouldn't do it as quickly as I'm doing. Yes, so that's okay. Later when you progress in solving problems like this, you will do it just much quicker. Yes, but it's okay if the important thing you solve this problem. If you spend not as little time as I do, it's okay. Okay, just try to if at some point if you see that you solve all these problems all the time, so you don't have problem like finding the solution. You just have problem of doing it too too slowly. Yeah? So just try yourself to do it fast every time. So you just try to solve this problem, only easy problems, only the problems that you're capable to solve. Yeah, you just try to solve them as every time you solve them faster and faster. Yes, you just measure how much time you spend and try to do it as fast as you can, and that's how you train basically your speed. So first you train just solving this problem, and when you feel like you're confident enough you can solve these problems, but it's just taking too much time, you train yourself to do it faster. That's basically it. But again, it's not a big problem if you do it not as fast as I do. Problem C. What's problem C? Problem C. Yes, problem C is, I would say, pretty classical problem. So what we need to do, we have one set of integer and another set of integer, and we need kind of cover this set with one set with another set. Yeah, let me show you what I'm talking about. So imagine the classic. Okay, different variations of this problem appears in different contexts. So you have two set of elements, let's say. So you have one set of elements and another set of elements. Yeah, they may have different lengths, the different sizes, and so on. So it doesn't matter. And you kind of need to cover these elements with these elements. So you can find the elements. So this is covered by this is covered by this, covered by this, covered by this. Yeah, and you cover by element, let's say greater or equal. So this should be greater or equal to this, greater or equal to this, greater or equal to this. That's greater. Yeah, of like you say, you need to put some elements in boxes. Yeah. So for each element, you need to find the box. So the size of the box should be not less than the size of the element. Yeah. So let's say these elements like AI, these elements like BI. So for each element AI, you need to find element BI, which is greater or equal to this element, and then arrange it in some way. Something like this. Yeah. And the way you solve this problem is by using greedy algorithm. Again, it's just a very classical thing. So if you see it the first time, it's okay to spend some time. When you see this problems like this for like 100th time, it's kind of obvious that you like see the problem and immediately think about the solution. Yeah, because you saw too many problems like this before. But if it's your first problem, it's okay. So the way we do it is just sort both the arrays and greedily assign elements from left to right or right to left, doesn't matter actually. So let's take the minimal element A. So we need to cover it with some element from array B. Yeah? Well, it looks intuitively correct to cover it with minimal possible element. Yeah. So let's find the minimal possible element which is greater or equal to my element, and just assign this element here. Again, this is intuitively correct. But again, when you have greedy algorithm, sometimes it's okay. Sometimes during the contest, it's okay. So you see, algorithm is kind of looks okayish. Yeah. So you just implement it and see if it works. It's usually better. That's okay. During the contest, you normally don't think about correctness of the greedy algorithms. You just feel like it, yes. And then you have wrong answer. Then you think, okay, maybe I'm wrong. That's how I usually do it. But actually, when you wanted to prove yourself how that this greedy algorithm works, how you think, okay, you usually think like this. The idea of greedy algorithm usually work like this. You do something, it's called like safe step in this theory. Yeah? So you're trying to make the operation which do not break the optimal solution. Yeah? For example, here, let's take the first element of array A. This ferment. So let's element X. Yeah. So this is the first element of array A. This minimal element of array A. We need to cover it with some element of array B. Yeah. So let's take the minimal element of array B. So there are two options. If this first element, so let's take this first element, Y. So if this first element is less than X, then it's less than all elements in array A. So X is the minimal element. So Y is less than all element array. It means we cannot use this array, this element anyhow. Yeah. So this element Y is unusable. Yeah. We can just remove it from array and continue. Yeah. Okay. So we can remove all elements which are less than X because they're unusable. So now let's pick the first element. So okay, these steps are safe steps. Yeah. So you can prove that this element is not used in the optimal solution. So if you remove it from the array, nothing will break. Yeah. So you just remove them and continue because it's safe. Yeah? Now let's pick the first element. If this first element is greater or equal than X, then I claim you can cover it with this element. Why it's always possible? No, because if you don't cover this element, you need to cover some another element. Yeah. And if this element is unused, you can just move from here to here. If this element is used, then you cover something like this. You cover let me see. So you cover this element of this. This is this, something like this. If you can cover like this, you also can cover like this. Okay. Okay, this is actually pretty accurate proof of the greedy algorithm. So you can formalize it a little bit better, but that's actually how you prove the greedy algorithm. So you just prove that each step you make it will not break the optimal solution. Yeah, and if you do it on every step, then like you have invariant. So optimal solution exists. So every step preserve this invariant. So in the end, you also have the optimal solution. Okay, I speak too much. So that's what we do in this problem actually. So in this problem, it's very similar. So we need to cover some elements of array A. So array A is yes, array A is what we need. Array B is what we have. Yeah. So we need to cover elements of array A with array B, and we need to. It's a little bit different. We don't need to cover all of them. We need to cover maximal number of them. Yes, and the rest we will just create. And you do it in the same way. You cover it kind of looks intuitively correct to cover only small elements. Yeah. So if you have some number of elements you can cover, you need to cover the maximal number of them. You only care about number of elements you cover. So it kind of makes sense to cover only small element. And that's what we do. We will go from small element to large elements and try to cover them one by one. And the rest we cannot cover. We will just add to the result. Let me finish it. So that's what I will do actually. So I will just, okay, I'm reading the data. Now I need to sort. They already sorted. Yes. I tried to sort both arrays because that's how I usually do it. But I saw that they are already sorted, so I don't need to sort them. Now that's it. So this is the code. Let's stop here. Stop here. So that's basically the whole code. So again, what we do, we go from left to right from array A. So this for loop works for array A. Now in this while loop, we skip all elements less than AI, and then take the first element greater. If we have no elements, then J will be equal to M. So we go to the end of the array B and stop there. Yeah. So if it happens, it means we have no elements. We can cover this. So we increase the result. Result is just number of elements we need to create. Yes. And if yes, we take these elements, so we just move again the pointer one position to the right. That's it. Again, it's a pretty classical problem of covering elements like this. So that's why I'm doing that first. But again, different variations of this problem exist. If you feel like problem, okay, the way you do it usually is just play with the problem. So you just look at the example and try to solve it by hand, and just think what you're doing, how you do it. Yeah. And if you think like it makes sense to do it in a greasy way, then you think, okay, why it may be true. So yeah. So think maybe greedy algorithm actually works. Then you think, okay, why the greedy algorithm actually, and which greedy algorithm works? Yeah, and then do it like this. Okay, let's go to problem D. What we have in problem, okay, problem D is again also very classical problem. So this sequence, let me stop here. So this sequence like this appears, no, or some different variations of this sequence. Let me show. So different variations of this sequence appear in different situations. Again, this is maybe the most classical one. So sometimes it appears in a string of letters. So if sometimes you have like sequence A, then you have A B A, then you have A B A C A B A, and so on. So every time you have two sequences from the previous step, and insert a new character in the middle, yeah, and so on. And you can do it infinitely. So you could A B A C B A, then D A C A B A, and so on. Yeah, and then so on E, and so on. Yeah. So you have this infinite sequence. Here do the same, but with numbers. So it's like 1 to 1, then 3 1 to 1, then 4 1 to 1, 3 1 to 1, and so on. Then you have 5, and so on, 1 to 1. And the question is to find the number in position k. What I will write in this problem is actually quite tricky solution. So it's not tricky; it's just cheating solution, I would say. The normal solution for problems like this is actually okay. Let me finish this solution. I will say what I'm doing here. That's it. So that's the whole solution. Okay, no, show me. Yeah, come on. Yeah. So let's look. So what I'm actually doing is just count the maximal power of 2, which k is divisible to. Yeah, and just output this basically power of 2. Why it's true? Because let's look at all elements in. So let's see. All ones stay in even positions. So they stay in position 1, 3, 5, 7, 9, and so on. Yeah. So every odd position has a number 1. Now, if you look at numbers 2, they stay here. So 2, 4, 6, 8, 10, 12, 14, and so on. Yeah. So they have step 4, and we start from position 2. So they stay in positions which are divisible by 2, but not divisible by 4. And so on. So every 3 stay in position which is divisible by 4, but not divisible by 8. And so on. So basically, this number marks the maximal power of 2, which now this position is divisible to. So that's why I'm doing this. Normally, I would have a different solution actually. So let me. Do I have? Let me see. Oh, this is different problem. So we will move to this problem later. So normally I would do it something like. Okay, let me show. So normally I would do problems like this in different so normally how would a problem like this? So you have some recursive structure. It's a recursive structure. So you kind of want to have a recursive function which calculates your result. Yeah. So let's write this recursive function. So how this recursive function will work? Again, imagine you have some string of the fixed size. Yeah. So now so let's say you have iteration. We have this problem here. Let me show. So in every let me get. Oh, let's try new. Let's do it like this. So we start from page 1, then we have 1 to 1, then we have 1 to 1, 3, 1 to 1, and so on. So these are steps 1, step 2, step 3, and so on. Yeah. So imagine you have step k. Oh no, so k is the number for us. Let's stay a step. We have n. So we have step n. Okay, let's have step n. So how step n look like? I have this letter n in the middle, number n in the middle, and then I have two strings from the previous step. So let's look at position k. Let's look at position k. If position k belongs to this part, yeah, I just have the same problem only with this left half of my string. If k belongs to this part, I also have the same problem with the smaller string. Yeah. So, yeah. So in the previous step, in step n minus 1, I have this small string. Now I have so these are all equal strings. So this string equal to this and equal to this. Yeah. So if my k belongs to this right half, I just calculate my index inside this string and just find the same position here. So I basically recursively call the same same thing in not string, sequence of degree n minus 1. Okay. If my k is exactly in the middle, then I know that number is n. So that's it. So basically you make recursive function which looks at your number and see which part you belongs to. So your string is constructed like this. Again, let me do it again. So in string of order n is constructed like this. I have string of order n minus 1, then I have number n, and then another string of order n minus 1. Yeah. And you need to find what number is in position k. So you just check which of these parts contains position k, and depending of which part contains, make different recursive calls. No, that's it basically. It's okay. So I would normally implement it like this. So let me see. So let's say n k. Okay, k is long. Um. Okay, let's do it like this. So I will say get from n and k like this. So I'll just show you how to do it recursively. Yeah. So I say int get int n long k. Now I need to find the length of the one of the halves. Yes. So to find this, to check which one contains position k, I need to find length of this part. Yeah. Normally I would just calculate it. Yeah. So I would just have array of lengths and calculate it recursively. But here I don't need to. So here I just know that the length of this part is just 2 in power of something minus 1. Yeah. So it will be something like 2 power n minus 1. Yes, something like this. No? Let me check really quick. So it should be minus 1. Yes, something like this. Yes. Yes, the whole part is this whole thing is 2 power n minus 1. Yes, and left has 2 power n minus 1. So I'll just do it like this. So the middle, okay, middle is just 2 power n. Let's do it like this. Minus 1. Well, I named them from 1, so the middle will be just this. So this is the middle. Now I check if k is less than the middle, I output the same of degree n minus 1. If k equals m, I just output n. And if not, I output the right part. So I output get of n minus 1, and my index in the right half will be k minus m. Yes, looks okay. Oh, boom, let me check. Boop. No. I say okay. I said n minus 1, but wrote n. Yeah, something like this. So that's how we normally. What? Oh, okay, makes sense. Okay, if I do return, I don't need else. So that's how we normally implement problems like this. It's kind of more general way to deal with 2 LL. No, 1 LL. So okay, so this is how we calculate powers of 2. So this number is moving the bits to the left. Yeah? So again, the number we need is 2 power n. Yeah. So in binary, it's like this. Yeah. So it's like n zeros here. So if you need to calculate power of 2 fast, you just take 1 and move it left n positions to the left. Yeah. So here I take 1 and move it n position to the left, n minus 1. So here I'm calculating 2 in power n minus 1. It's just cool thing, it is a very fast operation in the processor. So it's just single operation processor. So when you calculate powers of 2, you don't need all this binary exponentiation stuff like this. You just calculate this using bit tricks, and it can be done in constant time. It's actually very fast. So that's it. That's problem D. Let's actually look at your solutions. I'm curious, how did you solve this problem? Let's look. Like this. Oh, okay. So no, exactly the same solution actually, but like this. Okay. So you learned something new today. So you can calculate powers of 2 without this POW function. POW function is actually not as good because it is floating point number. So this POW function use floating point arithmetics, so it's not that accurate. But yeah, doing it in integers is actually faster and more reliable. Yeah, nice, good. Anybody solved it like I did? No. No, it's actually okay. So again, everybody used this safe approach. Okay, that's good. Yeah, let's see. Okay, nice. That's it. So that's problem D. Let's go to problem E. Oh, problem is fun. So again, different variations of the problem exist in. Okay, it's. I don't remember when that was the first time I saw the concept like this. So the problem like this. So what we have in this problem, we have basically sequence. So after you read the problem statement, it's written especially tricky, so you spend some time understanding what's going on. But the idea is very simple. So you have sequences of dots, yeah, and you remove all the dots except one. From every sequence, you remove all the dots except one. And this is your number of operations. And the question is, what is the total number of operations you can make? Yeah. Again, let me show you what I'm programming, because I will do it. Let me stop. That's okay. So you have this string. In this string, you have some. Basically, you only care about if it is dot or not dot. All other characters are basically equal. So I will just write x. X, let's say dot x, let's say dot x, something like this. So you can erase all the dots except one from every continuous sequence. So you have continuous sequence of dots here. From every sequence, you can erase all the dots except one. So you okay, but you erase this, you erase these two, you erase these three. Yeah. And this is your result, just number of dots you can erase. I will do it like this. So there's actually many ways to solve this problem. I solve it like this. I see that the number of dots I erase can be calculated like this. Is like total number of dots minus number of dots I can't erase. Yeah, I can't erase one dot from each sequence. So it will be number of dots minus number of sequence. Yeah. So I need to take care of these two values, total number of dots and total number of sequences. Yeah. So this is what's called C1 and C2 in this program. So this is C1 basically, and this is C2. So the first value is easy to track. So when you change one letter, one character, you just recalculate number of dots based on which character you change. And number of sequences also easy to track. So what's happening? So you have some character. So if you put dot in some position, which wasn't dot before, so you look at the sequence before, sequence there. So you basically you need to track these two positions. So if you have two dots, then you merge two segments into one. So number of sequences is decreased. If you have dot and something here, then number of segments is the same. Yeah. So I just extend this sequence to the here. And if you have two non-dots here, then you put a new dot here, so you create a new segment of size 1. So sometimes, okay, you have three options. Let me draw all three options. So when you put a new dot instead of some character, so you can create new segment. You can, if it's like this, so here you have +1 segment. So if you do it like this, you have nothing. The number of segments do not change. And when you have both, here you have dots, then you merge two segments into one. So you have -1 to number of segments. Okay? So just track these three. You look at the previous character, the next character, and based on these three situations, you track the number of sequences you have. Yeah, and that's it. So you track number of dots. It's easy. So you track number of sequences. It's a little bit more complicated, but still doable. Yeah. And now you have these two variables here, output C1 minus C2. That's it. Now I look at this. You can actually track the difference. Yeah, it does make sense to track both of them. I only care about the value C1 minus C2. Yeah, but yes, I added two x's to the end, so I don't care about these border cases. Yeah. So if I have dot in one of the edges of my sequence, I will just look at the previous character and will have this x. It's not the best program actually. Well, I will write here, but you will see. Okay. Yeah. So what I'm doing here, here I check. If I actually change the character, so if I change letter with dot or dot with letter, then I need to update my two values. So I see if I enter this dot, I increase number of dots. C1 is just number of dots, and then look how the number of segments change. So I see if I have two dots, I decrease number of segments. If I have okay, if I have dot and not dot, nothing changes. So I have this empty block of the if. Perfect programming, Pavel. Thank you. And if I have two non-dots, then I create new segment of size 1, so I increase number of segments. And then I just copied this block. Show me the program. Yeah, and then I just copied this block again. You see. So I just copy pasted this whole block and change pluses with minuses, because when you replace basically when you replace character some letter with dot, you do this, and when you replace dot with letter, you do absolutely opposite thing. Yeah. So I just replace this plus with minus, this minus plus, and so on. So basically, you do reversed operation here. Not the best programming, so I will not recommend to do it. So again, here I just do it differently, just to show you how you can do it. For example, okay, you can do it, for example, like this. So you here just to unify these two blocks, so you have one block instead of two blocks, like this. Also, not a great programming, I would say, but again, it's shorter, and usually a shorter program has less bugs. So that's how you do it. No, that's it. That's problem E. Let's see your solution. How do you solve this problem? Let's see someone. No, yes, no, something similar. Yes. Also, all together, also you have two identical blocks here. Yeah. You can simplify it, but again, usually for easy problems like this, okay, we have like 10-line block, and you copy it twice, it's still good enough. If you have like 50 lines of code and you copy it 5 times, not do it. Okay, so it's okay. Let's go to problem F. So problem F is actually surprisingly hard problem. So I spent some time actually thinking about it. So we have so we have picture like this, like here. We have basically some sequence of uh sequence of these towers, let's say, yeah. So how to say it? Sequence of what? Piles of cubes or something. Okay, and we need to find number of times we can remove all the bordering cubes. So in one step we remove all the cubes which touches the outside, and we do it until we have no blocks left. And the question is how many times we can do it until no blocks left. Good problem. Actually, this picture explains a lot. So what's happening? So let's look at the final block. So block removed in the last step. So if you look at the block which is removed in the last step, here, okay, I'm drawing actually the picture. It's perfectly synchronized. So it must have this pyramid of ongoing blocks. So if you removed it in the last step, then in the previous step you removed all these blocks. In the previous step you removed all these blocks. So you must have at least this pyramid of blocks. Yeah. And basically the question is, so if I want to remove okay, if the block is removed in later steps, this pyramid must be higher. Yes. So if you don't have this pyramid, then the block will be removed before. The question is actually to find the largest pyramid in your picture. So if you consider this picture, yeah, here in red, you find this triangle, yes, of blocks, and you need to find this triangle of the maximal size. That's actually that's already very non-trivial idea. Yes, so you move from problem count number of steps to problem find the maximal triangle. Okay, they actually look completely different problems. So this step is actually very non-trivial. So if you made a step, good for you. Now next, after you find this, you reduce your problem to this problem, you still need to solve it efficiently. Yes. Yeah. So how you do it? So I would do it like this. Let's look at this position. Yeah. So in all positions to the left, yes, I must have the height of this column enough to have a many. So again, if you consider on the left part of this triangle, yes, the maximal size is minimum of this value. Okay. Yep. Okay, hope it's clear enough. So again, if you look at position I and position J, yeah, so the maximal height you can have of this triangle, if you have this height in position J, is this. So like height of column in position J restricts you to make triangle of size greater than this. Then you look at all these restrictions and take the minimal of them. Yes, and it will be the maximal allowed size. Yeah, again, each position restricts you to make a big triangle. Yeah, you look at all these restrictions, take the minimal of them, and it will be if this is satisfied, then all other will also be satisfied. Yeah? So this also not non-trivial idea. So this is what I need to calculate. I need to calculate minimum of this value. Now it's a pretty standard step. So you look at this value and you combine everything connected to J in one side, everything connected to I to another side. Yeah? So from this value, I will combine everything connected to J. So it will be Hj minus J. See in this formula. Yeah. So now I rewrite my formula like this: I plus, so I is constant, yeah, here. So I fix the position I. So if you fix position I, you need to minimize this thing. So you take this I out of this scope, yes, out of this minimum, and you have I plus minimum of this value. And now you just need to keep track of this of minimum of this value for all j to the left. Yeah. And you can do it. You just go from left to right and maintain this minimum. And then we will do the same from the right. So you do this from the left, then we'll do the same from the right, and we will find all restrictions for position I. That's it. It will just give us the maximal size of this triangle you can make. I'm doing so. This R will be my result. So for every position, I will find the maximal size of the triangle. Mhm. Yeah, that's basically it. So again, you go from okay. So that's how I deal. Okay. So here, let's see. So this is my I track the left side of this triangle. So I go from left to right and maintain the minimum of these things. You see, this S will be minimum of these things. And then just update R is the minimum of these things minus I. Pop, pop, pop. I need to say minus I here. At some point, I will do minus I here. Okay, and here I will do the same, but from the right. Plus I, okay. I plus this minimum, okay. And when I go from the right, okay, I will draw another picture. Okay, I am right. So again, for every position in the right, I do all the same things, all the same minimum, but of this value. Yeah? Because j is to the right, so it's j minus I. It was I minus j, and that was j minus I. So again, I combine everything connected to j, it will be j plus h of j, see? Minus I. So I calculate minimum of hi plus I, it will be minimum of this thing. And then this minus I, see? Now for each position, I will calculate size of the maximal triangle. Now I just find the maximum of all of them. It will be the result. Yes, and here I have, here the answer is 2, but I said 3. It's actually for nice reason, because I incorrectly deal with the borders of my array. So I initiate these minimums as plus infinity basically here, see? But I don't deal, so in after I reach the end of the array, I have basically all zeros. So you have your array plus you have a lot of columns of zeros. Yeah. So you need to initiate your value as this column of size 0. Yeah. And you see it like this. So you basically think of it like this. So I have another column, and the height of this column is 0. Yeah. So the index will be -1, and the height will be 0. So I just replace height with 0 and index with -1. Yeah. And this is my value. So this is the value for the column, which is like virtual column, one position to the left from the left one. Just one. And here you do the same thing. So I need hi plus I. So I have column of size 0 in position n. See? That's it. Nice problem, actually. I'm surprised a lot of people solved it. Good for you. Let's check your solutions. S, F, 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 F. Okay, let's see. Okay, it's kind of the same. I'm not sure if you have the same idea, but yes, you calculate minimum of this, and here calculate it like this. Mm-hmm. Makes sense. Okay, so I'm not sure if there is another like completely different solution from this. So I think probably no, it's E, F. Probably all the correct solution are kind of similar to this. Okay. Uh-huh. Oh yes, pretty much the same. Good for you. Okay, we're moving to last two problems. So we have problem G and problem F, or problem H. Let's go. So problem G is kind of mathematical. I wouldn't say very mathematical, but kind of. One of the tricks of this problem is that the state that the string contain only characters A and B, which is very crucial to solve this problem, is actually right here. So you only see that you need to deal with strings of only characters A and B only here. Okay, that's fun. So without this property that you have only two characters A and B, this problem is much harder. I'm actually not sure how to solve it. Okay, it's still solvable, but it's just much harder. How is the problem? So first you need to see that every string which starts and finishes with the same character is a palindrome. Yeah. So again, what we do in this problem, we have the string, then we replace sequence of continuous characters as one character. So we have A and B B B. We just replace with A B A, and we need to have a palindrome in the end. And you can see that every string of characters A and B will be a palindrome if first and last character are the same. Yeah. So basically, we need to calculate number of substrings when the first and last characters are the same. That's it. That's it. Okay, if we only need to calculate this, imagine you don't have this property. You need to calculate odd and even length. So if you just need to have the property that it should be palindrome, then again you look at your string, yes, and you need to find pairs of equal characters. So if you have character n a, then this string is a good string. Yeah. If you just have this property, you just need to calculate number of characters a, number of characters b. Yeah. And then, like, if you have k characters a, then you can make pair of any two of them. So you'll do just k multiplied by k minus 1 over 2. So the number of pairs of characters a. Nope, okay. Okay, plus n in the end. Yes, because every single character is also a palindrome. Here we also need to calculate a number of palindromes of even length, number of odd length. So we also take care of parity of this length. It's actually also quite popular topic. So what's the idea? So you look at the length of this segment, and you look at the parity of the segment. You have segments of odd length, segments of even length. The thing is, the parity of this segment, of the length of the segment, depends on the parity of these ends. Yeah. So you have these positions I and j. Yeah. First and the last position of the segment. If they have the same parity, then you have the odd segment. If they have different parity, then you have even segment. Yeah. So again, why it's important? Because you move from a property of the segment to property of its ends. Yeah. Yeah. Let me see. So the parity of j minus I plus 1. Yeah. So we move to property like this. So let's say this is okay. Let's say it's odd if and only if j and I. Okay, let's like this. J mod 2 equals to I mod 2. Yeah. Okay, what's interesting about this? Why it's important to make observations like this? Because they move from property of the segment. So this property of the segment. Yeah. And these are two different properties of its end. Yeah. So you kind of split your. It's hard to track the segment. There are n square possible segments. Yeah. But it's easy to track its ends. There are just n possible ends. Yeah? So you kind of split this property of the how to say it. Basically, you split one composed property into two simple properties. Okay, hope it makes sense. So I'm just so this something like this happens in a lot of problems. You just need you need to track some strange property of some strange object, but this property is just composed of several small properties. Yeah, and if you decompose it, it's just much easier to keep track of them. Yeah. Okay. So what we're doing here, after you understand this. So how would you say so? So I need to calculate number of segments when I have two equal letters in two positions with the same parity. Mhm. So I just need two A's in two odd positions, one two A's in two even positions. Now let's count all of them. So let's count all positions of A, count number of even positions, count number of odd positions. Yes. So I need to so I need to let me show something. So we have some position, let's say A and B, A, B, A, B, A, B, something like this. Yeah? And the parity will be like 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0. Yeah. So let's look at positions A. So I have A in easy, boom, 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 boom. Yeah. So you have one, two positions in even positions, and 1, 2, 3, 4, 5 odd positions. We have two even positions and 5 odd positions. Yeah. So if you want to find, if you want to make a palindrome of odd size, you need to combine these two. There is only one way to do it, or you combine one of these 5. So number of ways to combine these 5 is just 5 multiplied by 4 and divided by 2. So you combine any pair of these 5 elements. And then you do the same with B's and so on. So okay, let me finish this. Is going. So what I'm doing, I will calculate number of A's in odd positions, number of B's in odd positions, and the same with even positions. Okay, I'm doing it like this. You can, okay, you need to maintain for this. Maybe it would be better to make a two-dimensional array like this. Yeah. You need to maintain 4 values. Yes, you can make array of size 4. It would be probably better here. But again, I'm doing it like this. So I maintain counts of A in both odd and even position, and counts of B in both in position. Like here I just count. Here I count how many elements are in all positions, and here I just calculate the result. So I calculate the result first in even length. In even length, you just need one of the ends being one parity, another parity. So I calculate product of count of A in even positions, count of A in odd positions. So every pair of this will give me even length palindrome, and this will give me the same for B. Yeah. And here, okay, this is not a great code. I'm not proud of it. Okay, it's okay. Can you spot the mistake already now? Again, let me show you. Number of ways should be like this. Yeah. So that's what I'm trying to calculate. Can you see the mistake? Funny enough, it actually passed all the sample tests. So authors actually made very good examples. So even this solution passes all the examples. Can you see the mistake? I go back. I read the statement, see if I missed something. Then I see, okay, what can I miss? Nothing can miss. Everything looks great. Nice. Yeah, so I checked that I understand the problem correctly. No tricks found. Okay. Okay, hope you found the mistake. Because now I will fix it. Okay, here, yes, I forgot these brackets, yes. Happens. And now since I copied the code 4 times, I need to fix it in 4 places. Luckily, they're close to each other. Yes. Sometimes when you copy big block several times and then you make a mistake, you need to fix this mistake in all blocks. It's complicated, but here it's actually not that. No, it's not that hard. So I'm fine. But yeah. So that's it. That's problem G. Like you see, the code is kind of short. Yeah, it's kind of math heavy, but not specifically hard. Okay, let's go to problem H. So the last problem. Surprisingly hard problem, actually. So we need, again, if you didn't read the problem, so why you didn't read the problem? So read the problem. What we need to do is to answer the queries. So we're given the array of elements, and we need to answer the queries. So every query give us the segment, and we need to answer. Let me stop actually. The query is the following. I need to find number of elements in the segment, but I only count for every value I count it at most k times. So given a segment, and you have some values of x. So if number of these x's is greater than k, then you count only k times. So it's maximum, it's minimum of number of x's and k, and just sum of them for all x's. Yeah. So if you have more than k elements, then only some k of them counts. Okay, my solution actually uses persistent segment trees because I can. I'm not sure if there is easier solution for this problem. Maybe there is some easier solution. I just use persistent segment tree just to show you how to do it. It's not that hard as it sounds. What is my idea? Let's do it like this. So let's have some elements. And if I have more than k elements, let's count only rightmost k of them. Yeah. So I will go from right to left here and count the first k elements. So imagine k equals to 3. Yeah. So I will count this element, count this element, count this element, but not this element. And I will maintain this array of zeros and ones. These zeros and ones will show me if I count this element or not. Yeah. So for every element, I will check if I need to count this element or not. Yeah. And I will count only rightmost k elements on a segment. Now, if I fix this right border here, I can go from right to left, yes, and mark all elements, only first k elements for every value. Now, if I have the query with this right border, like this query from L to R, the sum of this query will be just sum on this segment. So I just calculate sum of these zeros and ones. Sum of these zeros and ones will give me number of countable elements. Yes. That's it. Now I can answer all the queries with this right border here. So I have query here, I have query here, I have query here. Let's see, L1, L2, L3. So I can answer all these queries with this right border here. Now I can move this right border to the right. If I have element x, yeah. Now I need to count this element. Now I count this element. Let's move here. So I move right border from here to here. Now I count this element x, and now I need to stop counting this element. So this element is now 0. See? So I update this position. Let me show you. I update this position to 1. I update this position to 0. And now I can cancel all the queries with this right border. So if you, again, this kind of popular problem, so there was very similar very similar problem when you need to count number of unique elements on a segment. Yeah? So the classical problem looks like this. You have queries a segment. You need to count number of unique elements on the segment. It's basically the same problem, but with k equals 1. Yes. Here is a little more complicated because you have this k, but the idea is the same. So you maintain the segment tree of all elements which you count. Yeah. And when you extend this right border to the right, you need to include this element and exclude this element. Yeah. So you basically enable this element, yes, put 1, and you disable this element, put 0. So you make these 2 updates in your segment tree, and then answer the queries just like sum on the segment. Yeah. So you need segment tree, which allows you to change element and calculate sum on the segment. It's easy, normal segment tree, yes? The only problem here, you need to answer the queries online. So if you do it offline, you just go from left to right, move this right border, and answer all the segments with this right border. And eventually you will answer all the queries, if you can do it offline. In this problem, you need to do it online. So you have queries one by one. So you just do all the same, but make persistent tree. Yeah. So for every right border, you have the version of this segment tree. Okay, if you never saw persistent segment trees before, you can again watch my lecture about persistent segment trees. It's not very difficult. So again, you have the segment tree. Okay. If you don't know what is segment tree, learn how to segment tree. Segment is the most important data structure in competitive programming. So what is the idea? I have this segment tree, but then I try to update one value. For example, this value. I want to update this value. So let's match segment tree with some operation. Let's put something like 1, 0, 0, 1, something like this. So you have 1, 1, 2. So this is my segment tree for sum. Yeah. And then you change one value, for example, this. So you move from 0 to 1. And I want to maintain both versions. I want to find one version with 0 and another version with 1. So what you do, you basically duplicate all the nodes on the path. So you take this node, take its parent, duplicate it. Now you have this left child and this right child, and the sum is 2. Now for the root, you have the same left child, but this new right child, and the sum is 3. Yeah. So now you have basically two segment tree, yes, in the same picture. So the first segment tree starts from this root. So this is the first segment tree. It starts from here. And the second segment tree starts from here. Yeah. So we have 2 segment trees which share some of the subtrees. Yes. So every time you make one operation, you create log n new nodes in your segment tree. So in the end, you will create up to n log n nodes in total. And these n log n nodes will contain all the versions of your segment tree. And you can access them at any time. So at every time, you can access all the previous versions of your segment tree. Okay, if you never did this before, learn how to do it. I will just show you. It's kind of easy to implement. So I will implement it as a normal segment tree. Okay, it will take some time. Okay, I'll start by implementing all this stuff. So first, I see that I have this strange, like, query generation stuff. So I'll just implement this, so I don't need to deal with it later. Yeah, so I implement all this. Okay, I just carefully do what's written here. Yeah. Here I think too much. Now I will implement segments. Okay. So what I'm doing, I'm going from left to right and try to maintain the current state of my segment tree. Again, let me show you the picture. So what I will do, I will go from left to right, and for every right border, I will maintain the version of my segment tree which corresponds to this right border. Okay. To do this, I need to maintain all the positions for every element. So for every value x, I will maintain in this vector, I will maintain all its positions. So I take all positions, add another position, check if I have more than k positions, I need to disable this position. Yeah. Yeah. So I need to take this position and disable the element in this position. Now I will implement segment trees. So when you implement persistent segment trees, it's easier to do it using some pointers like here. So you actually need to have basically nodes and pointers to nodes. You can do it as pointers, you can do it as indices. I will do it as pointers, like, but up to you. So every tree is represented by its root. Basically, I will have here, I have array of pointers to the roots of my trees. First, I need to create empty tree. So I create empty tree, I create. So basically, how you create segment tree? You just go and create it. So I'll do it recursively. I will start if I have array of size, if I have segment of size 1, I just create a single node. If I have a segment of more than 1, I split it in the middle, recursively create 3 in the left, 3 in the right, like here. Here I forgot to return x. You need to return x. I will fix it later. So we create the empty tree, and now we make updates. Update will, okay, so I need to put 1 in position I. Yeah, so I need to enable this new element. Yes. And I need to disable element in position j. So I put 1 in position I and I put 0 in position j. Now I just implement this. Yes. Okay, this is basically similar with normal segment tree, but instead of this index, you have pointer to the element. Yeah. So the set is recursively say put this value in this position in this subtree of the segment tree. So this x is the subtree of the segment tree. L and R are the borders of the segment. So you see, if this again, if segment of size 1, you just assign the value and return. Why? What? Okay, I create new node. Yes, you don't need to change the value. You persistent. You never change the values yet. You create a new node and return. If size is greater than 1, then you split it in the middle. Check which one, left or right, contains value. If it's left, then you keep the right the same and update the left one. If it is in the right, you keep the left one the same and update the right one. Again, this code is very much similar to the code of the normal segment tree, but you just, every time you create a new node, when you change something, you create a new node. And now I will here I will just calculate the sum. Again, the code of the sum will be actually very similar to the code of the normal segment tree, but I will just, again, I will do it. I will give it the pointer of the root instead. Yeah. Yes, here we need to update the sum. Again, like a normal segment tree, you make recursive call, and then in the end, when you go back from the recursion, you update the sum. No, that's it. Now we need to implement sum. Sum is actually easy. It's always the problem. Then you have segment, you have two segments. You have segment you need to calculate and segment you have in it. And here I made the mistake again. Okay, I will eventually fix all them, but again, it's a lot of code. It's hard to write all that much code without mistakes. Okay. Here I spend a lot of time actually debugging this stuff. I'm trying to understand why I have empty pointer or null pointers. So I have some segment of size greater than 1, which has left sum but doesn't have right child. There's left sum, but doesn't have right sum here, you see? It doesn't make any sense. There shouldn't be something like this in segment tree. So here I don't understand how it happened. So my build should be wrong, yeah? So I see that, again, I build some tree, and the tree is not correct. So I go to my build function and find mistake in my build function. Yes, let's go back to, yeah. Just check that something wrong in the tree itself. So my build function must be wrong. Okay, here I forgot to return x. Yeah. Okay, here I have, okay, now I have no runtime error, but I have wrong answer on example. So I check what's going on. And the third number is different. Third number is 1, and it's just segment of size 1. So for segment of size 1, I return here 5 to 6, I return 4. It doesn't make any sense. It's greater than the size of the segment. Yeah. So this sum must be wrong. So I go to this sum and check again, just read it. Yes, and here I find this here I'm wrong. So the idea of debugging is to localize the problem. Yeah. So you're trying to find the first point when you have wrong result, and then check the basically the part of your code which produces this wrong result. Yeah. And then look for your problem around this area. Yeah. So that's it. That's the whole problem. Problem H. A lot of code, much more than we normally do in these contests. But again, the major part of this code is actually just implementing the segment tree. The logical part is actually this one. It's not very not very difficult. So I just go left from left to right here. Here stop. So here I just go from left to right. Make one change in segment tree, another change in the segment tree, and here in the answer request, just take the corresponding version of the segment tree and get one query. That's it. Nothing that really difficult. So this is the whole logic of the solution. The main part is actually to implement this persistent segment tree, but normally you can, if you implement it once, copy in your library. So next time, if you have similar problem, you can just copy it back and use. You don't need to write it from scratch every time, actually, like I did. But that's it. That's problem H. Let's look at your solutions. 2 people solve this problem. Good enough, actually. Oh, segment tree. Well, this persistent segment tree. That's something. Yes. I know how it looks. Yes. This is persistent segment tree. It's without pointers. You just use indices instead. Yeah. Okay. So you have all nodes have indices, and you have, instead of pointers, you have index of your left child, index of your right child, like here. Makes sense. That's how I used to implement it like this. Just recently, I moved from indices to pointers for some reason. I don't know. Maybe just as a challenge to myself. Yeah, good. And here I believe it's something. Let's say so. Oh yes, pretty much the same. Yes, you put 0 here. Yes, if it is then you put no. I know. Sure, what you put 0 and then you put 1. Okay, some sounds a little bit differently, but again, the whole idea I believe is the same. Good for you. Another solution. Oh, that's different. What's merge sort? It's probably merge sort tree, right? In merge sort tree, you basically have a segment tree but in every node you maintain the sorted elements of this segment. Like total size of all elements will be just n log n. Yeah. In every node you maintain not a single value, but a list of elements which belong to this segment. How will it help? I'm not sure how it will help solve this problem actually. Hmm. So what you put in this segment tree? False, x plus plus. Okay. If not first of I. Okay, for each element you know the leftmost position of this element. Rev up. Next, rev up. Okay, I think what you're doing here is the following. Let me show you. Let me show you. Okay, if I understand correctly what's going on here. So we take no, let's say for example, okay, so we have the segment. So for each element x, we move k positions to the left and find the element x. So if let's say k equals to again 3, yeah. So for each element, we look at the element k position also. So if we take this element in account, yes, we need so again we're taking only first k element. So we take this. So if we look at the element, look at k positions to the left. Okay, k positions. Let's look at all positions of element x and look at the element of x which has position like k positions to the left. Yeah. Okay. This element. Yeah. If this element belongs to our segment, then we shouldn't count our element. Yeah. So we should count only elements. So these positions, so they like here bi. Yeah. So this is bi. So this is I. So this is bi. So now we need to count elements I, which belongs to a segment from L to R, such that B of I is less than L. Yeah. So we need to only count element which has the k position to the left is B to the left from the left border of segment. So if it belongs to the same segment, we shouldn't count this element. Yeah. So this is what we need to calculate. Now, what we will do, we will maintain these positions bi in a what's called merge sort tree. Yeah. So for every, so we have a segment tree, but every element of the segment tree will contain not a single element, but all elements of the segment. So for in this node of the segment tree, we'll take these 4 elements and put them here in a sorted order. So here we have array of size 4. Here we have array size 4. Here we have array size 8, and so on. So every node will contain the list of all elements of corresponding segment in sorted order. Now, how you answer the queries? You look at your segment from L to R. Like a normal segment tree, you split it into segments. For each segment, you need to calculate number of elements less than L. You can do it using binary search. So you take this segment, using binary search, calculate the maximal prefix of elements less than L. Then in like in log square time, you will calculate the total your answer. Something like this. I believe that's what you're doing here. Good. That's actually very interesting solution. I would say it's a little more complicated than even the persistent trees. Persistent trees is kind of it's technical, but it's kind of not very smart, I would say. So you just take this persistent segment tree and just do it. This is much less trivial structure. Good for you for solving it. Yes, I'm impressed actually. Okay, I believe that's it. So thank you for watching today. Discussion. See you next week.